That was coming, hopefully. Um, this lesson today is a little bit difficult. Um, it has to do with transformations. And I have a whole lot of people that don't want to do the transformations, but this is something that we need to learn for future math classes. If you're going to take any other math classes, I have so many people that spend a lot of time making a table for some real complicated functions when all they have to do is learn the transformation formula. So I'm going to end up giving you a transformation formula and we're going to discuss, but I'm going to discuss them individually first. So I'm going to share a screen with you and we'll discuss the individual transformations first. So different families of functions. Before I show you different functions, I'm going to give you this vertical shift. Any function, no matter what the function is, and this is just some random function. Probably this would be a cubic type function, a cubed type function of some sort. But if you notice the original function, f of x, is here. And I apologize, I left my good pen at home, so I'm having to just do the best I can with this not so good pen. If the original function is here, then the transformation, if you have a plus c outside of the function, then you're going to shift your function up by that amount. If your original function is here, you're going to shift your original function down by that amount c. So a plus c is going to be shifted up and a minus c is going to be shifted down. Making sure you can see my screen. So for example, let's take this function y equals x squared. And we want to use that to get the graph of y equals x squared plus 4. Well, here's what I want you to do. I want you to learn your values for y equal x squared because they're always the same. And then your transformation, and I'm going to do it this way, is going to be adding 4 to the y value. It's a vertical shift. So take these points, -2, -1, 0, 1, and 2. And in MATLAB, you're only going to need the -1, the 0, and the 1. But I like to use 2 points. So you're going to take the -2 and square it. Let me do this. I'm going to do this on a different page because I'm not going to have enough room for this on here. So I'm not going to erase that, but let me just add another slide in. So here's what, if you were doing this by points, this is how you would do it. And the reason I'm showing you this way is in MATLAB, you're going to have to give the new ordered pairs. So for y equals x squared, you're going to have, so let's just start over here, -1, -2, 0, 1, and 2. Squared is 4. So your y value is going to be 4. Square -1, you're going to get 1. Square 0, you're going to get 0. Square 1, you're going to get 1. Square 2, you're going to get 4. So now let's go back to the previous slide. So I'm making a table. I'm making a table. I've got these ordered pairs. My function says, and I'm going to go back to the other page. I just want to make sure everybody's got the table done. So I'm going to go ahead and write these. Y equals x squared. I know I'm making this more complicated than it needs to be, but here's the reason I'm doing it. I'm going to do this because I want to show you that with a vertical shift, all you're going to do is add values to your y. So those are the ordered pairs I got from that table. So these, if I graph those ordered pairs, this is what I would have. I would have 0, 0 would be one of my points. I'm going to use a different pen for that, maybe. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. This one is just x squared plus 4. So that's a vertical shift. All you would need to do is come back over here and add 4 to all of your y values. So your new shifted or your new graph would be add 4, we get negative 2, 8, negative 1, 5, 0, 4, 1, 5, and 2, 8. So those would be your new ordered pairs for your vertical shift. Now, why did I go through all that? I already had the picture here, and I could have just shown you that all you have to do at this point is just go up 4 and plot all your points again. So all of your points are just going to shift up by 4. So you take a parent graph and then we just shifted everything up because of that plus 4. All the points get shifted up 4. So it's that simple if you have the graph or you can get the graph. So I guess my point being to you here is if you will learn your table for y equal x squared, your points are always going to be negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Then if you have a horizontal translation, you change your x values or you just move your ordered pair by changing your x values. If you have a vertical translation, you change your y values. The reason I showed you this is what you have to do in MATLAB. So you can't just necessarily take the graph. You're going to have to list the ordered pairs for the parent graph, and then you're going to have to list the ordered pairs for the shifted graph, for the translated graph. Now, I'm going to stop sharing this page with you for just a minute because I want to go into your Canvas course and show you a couple of things in there. So before we move on, If you go to your modules, and here, these are where all of your videos are. Now, the ones in red here are just some videos that are from YouTube. You can click on those if you need help with graphing, if you need help with domain and range other than what I've already given you or my videos. Graphing absolute value. If you need to see that, there's another example. There are all kinds of examples of these. I've done a math lab demo here. And so this math lab homework number 2 in 2.3, it will work it'll show you, I went through the steps of doing number 2. And so it shows you how to do that in math lab. So if you're having trouble doing your math lab for 2.3, and some students do, then you should click on that and just watch me go through the steps of working that. I'm going to go to this worksheet in just a few minutes, to this transformation of quadratic and absolute value worksheets, because I want to show you different translations. But before I do that, I'm going to go through a couple more slides with you. So that's where you can find information of the math lab. All right, now I am back to the slides here. So there's the graph. I just showed you how to do the ordered pairs. Now this one is an absolute value. An absolute value, the charts are always the same on it as well. Take the absolute value of -2, you get 2. Take the absolute value of -1, you get 1. Absolute value of 0, you get 0. Absolute value of 1. Absolute value of 2. So those are your ordered pairs for y equals absolute value of x. So we have -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And remember when we were in the last section, we said we'll just make sure that we get a V. Well, in the last one, we were just taking any function and making a table. In this section, and I'm sorry, my pen's not real good. In this section, we are actually taking a parent graph and then we're doing a translation on that parent graph. So what does this tell us to do? Well, this is a vertical translation. I'll show you what a horizontal translation looks like. Well, what you're going to do in this one is all the y values, from all the y values, you're going to subtract 3. Because it's a vertical translation. So if I take all my y values from the parent, so this is the parent in black, and I subtract 3, my new ordered pair, the x doesn't change. It's going to be -2, -1, -1, -2. So I'm subtracting 3 from the y value. 0, -3. 1, -2. And then 2, -1. if I plot those points, what it does is it shifts all these points down by 3. So my transformed graph looks like that. So you could just graph the parent and then move all of your points down 3. So why don't I just let you do that? Because you have to do this in MATLAB. So you need to be able to translate by moving, shifting the graph, but you need to also be able to translate by shifting the points. So you need to know what to do with the points. So if it's a vertical shift, you're going to shift down. Now I'm going to show you a horizontal shift. Now this is a little bit more confusing because like with the circle, when we had something in parentheses, when we had the circle, we had, I'm going to try to show you some of you never learned about your circle, but we had something like that. So a circle with center 0, 0 looked like this. And a circle with a different center meant that you're going to take that 0, 0 center and you're going to shift it HK. But it was always in the opposite direction of that sign. So if that sign was minus, if this was X minus H, then that meant we shifted to the right. So anytime you have something stuck in a parentheses in a function, the shift is going to turn the other way. It's going to be the opposite of the sign. So if you have a plus C here, it's going to shift it to the left. If you have a minus C, it's going to shift it to the right. And that goes for any function, anywhere, ever. It goes for a non-function too, as you can see with the circle, because with the Y value, that K was inside the parentheses. So that meant that shift was the opposite direction. So anytime you've got a number trapped with X or Y inside of a function, but mainly inside of with these, they're going to be functions. So you're not going to have Y squared or something like that. But this was just an example of something we already did. So all of these are going to be functions. So anytime you've got a number trapped inside with X, then that function is going to shift in the opposite direction. That's going to be your horizontal shift. So we're going to take a look at this for a second. I'm going to summarize all these translations in just a few minutes, but right now let's take a look at this. So I'm going to use my table like I've been doing and the ordered pairs on the table. And this is really the easy way to graph a square root, because square roots get kind of hard because you want to find perfect squares, and that's hard to do when you've got something in there. But with the square root of X, I can't go lower than 0. So my points are always 0, 1, and 4, the first 3 perfect squares, if you call a 0 a perfect square. So if everybody's listening to me, if anybody wants to learn something here, the square root function always has these points. The X values are 0, 1, and 4, and the Y values, you just plug the X into the function, you get 0. So you can see why I skipped 2 and 3, right? Because 2 and 3 are radicals, irrational. I would have to approximate that. I don't want to approximate. I want to put exact points on. So this is my parent. because it's a square root function. So my parent graph is y equals square root of x. I plot my points. I'm going to plot 0, 0, 1, 1, and 4, 2. That's your square root graph, y equals square root of x. Now, inside this radical, I have something that causes me to shift the graph horizontally. Horizontally is along the x-axis. So if it's trapped with the x, then your shift is horizontal. Now, I have a -4 inside of here, so that means it shifts, the graph shifts to the right 4. Opposite direction because it's trapped inside of that function, inside of that square root with x. It could be trapped inside of an absolute value. It could be trapped inside of a parenthesis, but that's a square root and it's trapped. So that shifts 4 to the right. So what I would do with my ordered pairs is I would take my x values, and since I'm shifting to the right, I would add 4 to my x values. So my shifted points would be 4, 0, 5, 1, and 8, 2. So I would be moving all of these points to the right 4. And then I have to come outside of my graph a little bit to get that one because my graph only went to 7. Now in a different color, what if this had looked like y or g of x? Let me call it h of x since I'm going to change it. What if I had had h of x equals the square root of x minus 4? Can somebody tell me, either unmute yourself or tell me what would happen to that graph? You can unmute yourself or you can type it in the box, but would someone please tell me what would happen to that function? You would start with the same parent graph, and then what would the -4 do in that problem? Is anyone there? Okay, I see a couple people typing. Good. Okay, I got a few answers here. You're right. It would go down. It would go down because the 4 is not in the parentheses. So when it's not, the -4 is outside the parentheses or outside the square root. So that means it would go down 4. So I see some people got typed in their answer. So I'm going to write this. I'm going to write another slide here real quick because I really want you to see this. It's so important that you don't miss this right here. So this parent graph, these are all transformations. This one shifts, so I'm just going to put shift here. Okay, and then I'm going to write it. This one, I hope you can guess because we just did it, shifts 4 to the right. This one shifts 4 to the left. This one shifts 4 down. This one shifts 4 up. So what's the difference? Inside of the square root is going to give you a horizontal shift one way or the other, and it's opposite direction of what's there. Outside the square root, you see that parent function's there and then -4. That's when you shift it down, or +4, you shift it up. So I wanted to add another slide and show you the different types of either vertical or horizontal and how to tell the difference, because it gets a little confusing when you start putting these all together. You can have reflections as well. So a reflection is going to go, it's going to reflect if the negative is in front of the function itself, then it's going to reflect about the x-axis. If the negative is inside of a parentheses with x, it's going to reflect it over the y-axis. And then if there's a number in front of the function, you're going to get a stretch, a vertical stretch. If there's a number in front of x, you're going to get a horizontal stretch. I'm going to do some more examples so you'll understand. If you printed these slides, I do not recommend doing the transformations the way that the slide said. So I have changed the slide. I recommend doing all vertical stretching or shrinking and reflections. I would do those first. I would do the vertical stretch or shrink first, and then do the reflection, then do the horizontal and vertical shifting last. Now, what does all this mean? Here is your, going to give you a transformation equation. Let me not do that. That's confusing to use function notation. So let's talk about some different kind of graphs we might see. Then we'll pull up a slide, another page. Parent, and put the parent here. These are the different parents we might see. Y equals X. That's a line. And we've already been graphing lines. We've been graphing transformational forms. You just didn't know it. Point slope form is a transformational form. We might have y equals x squared. That's a quadratic. That's a parabola. I would suggest writing these down. You might have y equals x cubed. That's a cubic. It makes kind of a snake form. I'm going to give you the going to give you the what it looks like. So let me just sketch a little line out here and then a little parabola here and then a little cubic here. Looks kind of like a snake. Absolute value. Looks like a V. Notice the quadratic has curvature. It curves around. Not my best pen, so I apologize about the sloppy writing today. And then you might have y equals square root of x, and square root always starts at a point, and we looked at the domain of that, and we know the square root can't go to the left, so we just put a dot there. And we just curve it around a little bit. So this is your square root. And then every function has a transformation form. And it makes things a lot easier. So transformational form. If you notice, that looks a little bit like the point slope form. If I subtracted k from both sides, I'd have y minus k equals ax minus h. Well, the a here is the slope, the k is the y-intercept. So this is just transformational notation because we use the h and the k. If I have a quadratic, it might look like this. I have a cubic, it might look like this. Absolute value. And I don't really do horizontal stretches because they don't occur very much. And we usually factor that out anyway if it's with the X. So I'm not going to do the B in front of the X right here. For this chapter and this section, these are your transformational forms of equations. I just want you to know that this transformational form builds. So in the next chapter, not chapter 3, but in chapter 4, we're going to have to apply this to exponential functions and logarithmic functions. So if you'll learn the transformational form and what it really means, it'll make that chapter a whole lot easier because you'll understand when we start doing transformations of those functions. So I'm going to come over here to a slide and I'm just going to pick one of these. Doesn't really matter because you'll notice they all look the same, don't they? They just, the function changes. So they all look very similar. So I'm just going to pick one of them like the quadratic. And I'm going to summarize everything here. A gives you stretch, or shrink. Think about stretch as like stretching a rubber band vertically. It's vertical stretch. Think about shrink as maybe taking a stiff kind of spring and pushing it down or compressing it down. It's pushing down on that spring. So shrink. If if A is negative, you're going to get a reflection. And I know this is a lot, but it all makes sense if you think about what's going on. So a negative just means you reflect. So those are the first things that I do. If I have a stretch, I go ahead and make a new graph is basically what I do. Now, x minus h, this is your horizontal translation. Notice it's inside the parentheses. So minus h shifts to the right, plus h shifts to the left, always the opposite. Okay, you think about minus h should go to the left, but it doesn't because it's trapped in there with x. Anytime it's trapped in the parentheses, it's going to shift in the opposite direction. And then k is going to give you your vertical shift or your vertical translation. This is really not hard. It's just probably new. So plus k shifts the graph up, minus k shifts the graph down. And you could have all of those translations all at the same time. I'm not going to do one just yet. I will in just a minute. First, I'm going to do one that looks like this. So y equals 2x, y equals negative 2x squared. So I'm going to show you what you would do with your table to take care of this. You would start off with your parent graph, y equals x squared. So nothing happens to x here, right? The x is just x squared. Nothing really happens to that x. But out here, that tells me I have a vertical stretch because the number is a whole number, an integer. I have a vertical stretch, and the negative tells me I have a reflection. So here's what you need to do. You need to make you a table, and I'm just going to use 3 points this time because that's what Math Lab does anyway. I'm just giving myself a little more room. So I'm just going to use this time -1, 0, and 1. You should memorize these so you don't have to do this every time. So when you have an x squared function, you're going to have -1, 1, 0, 0, 1, 1. So that's your ordered pairs. So I'm just going to list them over here. So if I wanted to draw my parent graph, that's what I would draw first. The -2 stretches the graph and it reflects it. So what you do is you take this value right here and you multiply it by -2. So you get -2, still 0, and then you get -2. So the new points are going to be -1, -2, still 0, 0, and then 1, -2. Parent, transformed. I'm just going to call it transformed. Well, can you write transformed there? I hope I haven't lost my other pen. I'm gonna have to order one if I did, because I can't write with this thing very long. So I'm gonna do both. I'm gonna graph the parent graph, looks like, so I can show you how this works. So it would be 0, 0, 1, 1, and I know if I did one more point, it would be 2, 4. So this would be my parent graph. And then my transformed graph would be here. So I would have -1, -2, 0, 0, and 1, -2. And if I had one more point, I would have the 2, 4. It would end up being 2, 8. But so it stretches it vertically and it reflects it. This is what you need to be able to do for Math Lab, because they're going to ask you for those ordered pairs. So just make sure you know how to get your new ordered pairs that way. Now, before I go on, do I have any questions from anybody? Can anybody think of anything you don't get? I tried to write transformational up there, but I couldn't get my pen to write it out, so I did the best I could. Does anybody have any questions pertaining to what we've done so far? Am I going too fast? Am I going too slow? All right. I'm going to give you a problem, and I want any of you to tell me what you think. I want you to tell me what you think the translation of this is. We'll talk about the parent graph and all that, but I want you to see if you can tell me what the translations are. Like if you see a vertical translation, you can just say up or down, whatever. If you see a horizontal translation, you can tell me left or right, whatever. So from that, we see a square root. So our parent graph is going to be the square root. What transformations do you see by looking at that? Anybody? Or everybody? Everybody can respond. Anybody there? Are y'all there? Did y'all go to sleep? Did y'all leave? What? Okay. Telling me that y'all agree with the people that typed reflection, 3 to the right, and up 1. That is exactly right. So you would start with your parent graph. So y'all have done this before, or either y'all catch on quickly, one of the two. So the parent is y equals square root of x. We know the parent graph, I'm just going to write them, okay? So this is xy. So we know the parent is 0, 0, 1, 1, and 4, 2. And I left a little room there because I'm getting the square root. So I use 4, 2. So that's my ordered pair. The reflection says that I need to make all of those negative. So I'm going to do the reflection first. So that's going to still give me 0, -1, -2. Then this tells me to shift to the right 3. So that means I need to go to the x values and add 3. Oh no, I'm writing on my wrong screen. So let me just fix this. I'm going to go to this won't let me. It's not going to let me erase. This is where I messed up. Okay, well, I'm just going to have to write on this. Sorry about the scribbling. So adding 3 to my x values is what I'm doing the translation. I wanted to change colors, but I couldn't change colors. And then after I've already reflected, then I need to add 1 to my y values. So do y'all see what I'm doing there? Does that make any sense? So my ordered pairs for my translated graph are 3, 3, 1, 4, 0, and 7, -1. So ordinarily, if I hadn't written all over the screen, I'm going to have to actually get out of here and come back in to fix this too, I think. But anyway, my parent graph was, we said 0, 0, 1, 1, 4, 2. My transformed graph was a reflection, a shift to the right, and a shift up. So my new points were 3, 1, 4, 0, and 7, -1. So that's what it looked like when I did the transformation. That one would have probably been harder to do if you didn't do the ordered pairs. So notice what I did. I took my parent function 0, 0, 1, 1, 4, 2. That's always going to be the points for y equals square root of x by itself. I added 3 to the x values and I did my reflection. Then I added 1 to my y values. So that's why I say do the reflection first, because you want to, if you've got to get the new ordered pairs, you don't want to get yourself confused. So go ahead and do the reflection, then do the vertical shift upward. Okay. Now, if you had had a number in front of that radical, you would have just done that with the negative. So if you'd have had a -2 in front of this radical right here, then you would have just said, instead of just multiplying by -1 here, you would have multiplied by 2 or by -2. So do your stretch, shrink, and reflection. Do that all in one step with your ordered pairs. You'll come out a lot better. Now, I'm going to leave for just a minute and come back in because I think that's the only way I'm going to be able to get rid of this stuff that I've put on my screen. I figured out how to get the eraser up there. Act like I don't have, like I can't even walk around sometimes. Okay, so now back to my PowerPoint. I do have one question for you though. Do y'all understand the transformation? So do I need to go over? I'm sorry. You had a, yes, because of the negative before the square root. Sorry, I didn't see it. Um, do I need to do another one? Are y'all okay with this, or could you use another example on this? I know y'all didn't have to leave, just I needed to leave. I got it fixed. I figured out how to do it. I was just being stupid. So, do y'all need me to go over anything else as far as the translations? Do y'all need another one, or are you good? Okay. All right. So, we just have a couple more things to talk about. They really just have to do with even and odd functions and symmetry. And this is kind of just learning. You guys have to memorize it really. An even function, you have an even function if you plug in a -x everywhere you have an x and you get the same function. In other words, the y value is not going to change if you replace x with -x. If you have an odd function, if you plug in -x into the function, you're going to get the negative of the function. And it's easier just to show you what is meant here. Also, even functions are symmetric about the y-axis, and odd functions are symmetrical about the origin. So identify whether this is an odd, even, or neither.
Miss Etheridge, we can't see your
Okay.
screen.
I'm so sorry. I forgot. I'm sorry. Thank
Thank
you.
you.
Okay, so this is what I was doing, and you have access to these too. You can go back and get these from the module if you don't have them printed and you would like to print them, or you can take notes from them, whatever you want to do. But this is the definition of an even function. So when you plug a negative x in for x, you still get the same function. It's basically the same. And if you plug a negative x into a function, you'll get the negative of the function if it's odd. So the easy thing is just, again, just to show this to you. So it says identify whether the function is even, odd, or neither. If you plug a negative x in, and this one's pretty much already done, that means everywhere you have an x, you're going to put a parentheses and you're going to plug in a negative x. You got to use a parentheses because order of operations says I need to do that exponent first, which is going to make that a positive x squared. So I end up with the same function. So that means that f of x is the same as f of negative x. So you get the same function whether you put in an x or a negative x. That's what happens with an even function, like a parabola is an even function. In other words, symmetrical about the y-axis, and the x value here on this side has a matching x value over here on the same distance from the y-axis. So that's a positive x and that's a negative x. The y value is the same. So that's an even function. Now, if you're listening, I'm going to tell you a shortcut without you having to actually plug it in. If you take your function and you look, I'm not writing this down, so if you want to know, you better listen. If you look at your exponents and all of them are even, then the function is going to be even. Now, a constant has a zero exponent. Zero is even. Okay, so a constant has an even exponent because zero is considered even. So using the shortcut, I see a square exponent, x squared is even exponent, and 6 is constant, so the exponent 0, so that's even. So that's an even function. B, exponent 3, exponent 1. Both are odd. So that's an odd function. That one's going to be symmetrical about the origin. And then C, I have an odd, I have an exponent of 1 and an exponent of 0. So it's going to be neither. It can't be both. So if you get one, then then you know it's even. So I'm going to plug in a negative x here and see what I get. Notice I get the exact same thing I started with. So that means this is even. I also could look at the exponents and tell that was even. What if I plug in a negative x to this one? Well, that's going to give me 7 times negative x cubed. When I cube negative x, I still have a negative. So that's going to be negative 7x cubed plus x. Notice how this is positive, this is negative, this is negative, this is positive. Otherwise, everything else is the same. The signs are opposite. So what that means is f of x, f of negative x equals the negative of the original function. So I plug in a negative x, it changes all the signs. So that's odd. Again, if you're listening, I'm not going to write it down because there's the mathematical explanation. But if all the exponents are odd, then the function's going to be odd. What if I plug a negative x in here? Well, the x has an opposite sign, but the 1 doesn't change. So I don't have, I have neither here because I don't have the same function and I don't have the opposite function. So I have neither even nor odd. I really just, I don't get an opposite function because the 1 doesn't change signs. So even functions are symmetrical about the x-axis, and I showed you y equals x squared, how it was symmetrical. And what it means is the side on the left is a mirror image of the side on the right. So you could reflect these points over and you're going to get the same x value on both sides. An opposite x value, but you're going to get the same y value. So this point here is x, and this is the matching point, negative x. So that's symmetry. You could take the mirror image or fold one side over the y-axis. You could fold the right-hand side over to the left side, and it would match. That's symmetry. Odd functions like y equals x cubed, they're symmetrical about the origin. So you could take an x and a y here. So this would be xy. Sorry, making a mess. Don't like this pen. I hope I don't go off without it again. So this would be xy. And if I reflected that over the origin over 0, 0, I would get a point over here. That would be negative x, negative y. So you could just sort of reflect that over the origin and you'll get the opposite point. That's an odd function and it has symmetry about the origin. And that's all I need to go over today, except for I need to tell you about Tuesday. Unless you want me to go ahead and start with the next section. But Tuesday, I need to be out. I've got to take my son to a doctor's appointment in Mobile in the afternoon. So I'm going to be off next Tuesday afternoon. So what I would like for you to do instead of meeting with me is go into Canvas, into your modules, and watch the video for 2.4 and 2.5. Because I'm not going to go over the whole thing again. So I need you to watch. I'm going to send an email out because over half the class is not even here in attendance of the last session. So I'm going to send an email out. So hopefully they're watching the videos anyway, since they don't bother to come to class. Probably not going to pass either, but that's beside the point. I am going to go over a little bit of this, like maybe range and domain stuff that you might not get from the videos exactly. an inverse function. So I'm going to go over these just a little bit next Thursday, but I will be out Tuesday and I need you to watch the videos for 2.4 and 2.5. Okay. Any questions on that? I think you'll be fine by watching the videos, but if there's something in the videos you don't understand, then you can email me or you can let me know Thursday that you need me to go back over something. So I won't be with y'all Tuesday. I'll see you in a week from today on here, and just let me know if you have any questions. Y'all have a great day.